Okay, welcome back. What I want to look at today is engineering mathematics, periodic functions and periods. Now, amplitude. Amplitude is the name given to the maximum or peak value of a sine wave. Each of the graphs shown in figures 23.13 to 23.16 has an amplitude of +1, i.e. they oscillate between +1 and -1. However, if y equals 4 sine A, each of the values in the table is multiplied by 4, and the maximum value and thus amplitude is 4. Similarly, if y equals 5 cos 2A, the amplitude is 5, and the period is 360 divided by 2 equals 180 degrees. Now remember the amplitude will be 5. The 360 divided by 2 give you 180 degrees in reference to the cycle. Now what I've done first here is to look at the problems first before I've actually looked at the graphical representation in the form of the waveforms. So, problem 4. Sketch y equals sine 3a between a equals 0 and a equals 360 degrees. Amplitude equals 1 and period equals 360 divided by 3 equals 120. Now again, you can consider this as a three-phase motor who will have their coils 120 degrees out of phase with each other. Or it could be a generator which will still have the same 120 degrees out of phase shift between each coil. A sketch of y equals sine 3a is shown in figure 23.17. Now problem 5. Sketch y equals 3 sine 2a from a equals 0 to a equals 2 pi radians. Now again, we're looking at amplitude in this case, purely the amplitude. Okay, and we know that the amplitude here in this case is 3 . Oh, sorry about that noise, it's just my sweetie paper. Thank you. Okay. Now, amplitude equals 3 and period equals 2 pi over 2 equals pi radians, or pi rads as we would say, or equals 180 degrees. Now remember that pi equals 180 degrees. A sketch of y equals 3 sine 2a is shown in figure 23.18. And please note that 3 sine 2a is simply in reference to the amplitude. And here we have figure 23.17, y equals sine 3a. Okay. In this case, we have a peak value of 1, or maximum value of 1. Now in y equals 3 sine 2a, you can see we have now a maximum value of 3 in respect of sine 2 times a. Okay. Now remember that bear in mind that as you deal with this yourselves, you would have dealt with this at level 2 for purpose of electrical principles. Then you would do more of this at level 3, where you will be required to draw out the graphical representation of those waveforms, and you will do a lot more practice and examples at level 3. Okay? But you should have been introduced to it at level 2. Now problem 6. Sketch y equals 4 cos 2x from x equals 0 to x equals 360. Now, for me, I would normally produce a table, okay? And I said that automatically because x equals 0 to x equals 360 degrees. Sketch y equals 4 cos 2 times x. Okay? So for me, I would produce a table overall. But I haven't done this in this case because it's aimed at yourselves at level 3 and some level 2s who would have done a lot of this themselves. So you're able to do this and apply this calculation for your own edification. Okay? So you don't really need me simplifying it any further, because if we do anything further, it's just going to be simplified. Amplitude equals 4 and period equals 360 divided by 2 equals 180. A sketch of y equals 4 cos 2x is shown in figure 23.9. 23.19, my apologies. And here is the waveform for that. Here you can see you have your peak value, y equals 4 cos 2x. Okay? And you've been given the values of x, which you would have produced a table for, so you can plot the graph basically. All I've done here to show you the finished product overall, but you should be able to produce a table, plot the graphs, and actually by hand on graph paper, and I would strongly suggest that you do that for yourself overall. Okay. Okay, so let's just recap a little bit. Okay, y equals 3 sine 2a. Problem 6. 4 cos x to the x equals 0 to x equals 360, and I would have produced a table for that effect. Okay, I haven't done it in this case because at level 3 these are things you would be doing for yourself and you should know how to do by now, so I don't need to simplify it any further. Now make sure you've done it. I would like to see it. When you've done it, show me. Okay, I'm just looking now at problem 7. And again, I said I've taken problem first before anything else. Sketch y equals 2 sine 3/5 a over 1 cycle. Amplitude equals 2. Period equals 360 divided by 3/5 equals 360 times 5. Okay, divided by 3. Now equals 600. Now here, we simply multiply out top and bottom by 5. And when we multiply top and bottom by 5, it will cancel out and it will actually leave us, as it says, 360 times 5 over 3. Okay? You multiply both sides by 5. Or top and bottom, I should say, by 5. Now make sure that you have actually put this into your calculator and that you've actually divided and got the answer 600. Do not assume this answer to be correct, because what I've done in some cases is actually putting an incorrect answer so that you can then, when you try to do a calculation further on, it doesn't actually work. So make sure you calculate for yourself. A sketch of y equals 2 sine 3/5 a is shown in figure 23.20, and the waveform again should be plotted. Again, produce your own table. And that's the waveform. It becomes a sinusoidal waveform, AC. Okay? And it's 180, 360, 540, 600 degrees. And the peak value, or maximum value, is 2. Now, with problem 7, you will see they have multiplied both top and bottom by 5. Having multiplied the bottom by 5, it will simply cancel out, leaving you with 360 times 5 over 3. And that's what we have done at the top. So let's go back and have a look at what we've done. And this is where we've done it here, okay? That's what we've done here. But I've simply expanded it further to show you that it was how it was achieved, okay? Sorry, it's just my sweetie paper crackling again. Okay. Now here I've simply showed you how a table can be produced for a, 3 times a, and the sine of 3a. Okay, and that's my table effect there for yourselves. Okay. Now again here, for the table you have the values of a, then you multiply the values of a by 3. This is where 3 times a comes into play. You then find the sine of 3 times a, and the values are given in the table. Okay. I produce the tables in Microsoft Excel, by the way. Okay. Now this is figure 23.17, okay? Figure 23.17. And it's the periodic function problem 4, sketch y equals sine 3a. And if you remember, we did problem 4 and you have a sketch upstairs for it up above previously shown. So feel free to look back at that. But I just thought that it was imperative that I showed how this can also be calculated in regards to the complete cycle. Okay. Now remember that there's slight variations when you're doing certain things. Okay. Right. Well, this graph looked like at the time I did it, but heaven knows, looking at it now, probably still is right, but I won't stress too much on that all day long. If not, you can do it better than me. Okay. Now, lagging and leading angles. Lagging and leading angles. Now, lagging and leading angles. A sine or cosine curve may not always start at 0. To show this, a periodic function is represented by y equals sine a plus or minus delta, or y equals cos a plus or minus delta, where delta is a phase displacement compared with y equals sine a or y equals cos a. Now what it's trying to say here is that it's trying to indicate any angle at this stage, that it could start at any point or at any space in that point. It doesn't actually have to start at 0, it could start 30 degrees, 60 degrees, 90 degrees, which would make the waveform either leading or lagging. By drawing up a table of values, a graph of y equals sine a to a in respect of 60 degrees may be plotted as shown in figure 23.21. If y equals sine a is assumed to start at 0, then y equals sine a to 60 degrees starts 60 degrees later. So if starting 60 degrees later, i.e. has a 0 value 60 degrees later. Thus y equals sine A 60 degrees is said to lag y equals sine A by 60 degrees. In this case, it would be lagging because it's starting 60 degrees later than the original waveform. Okay? So it is lagging. Now again, read this for yourselves. Take down the extract information, make your own. Do some additional research. Look at some electrical principles books. There's quite a good few of them around now. See how they have adapted or shown how to calculate in regards to lagging and leading angles. Okay? Find your own method. Now, we all learn in different ways, and your principle of learning method may be different to others. So therefore, you will need to make the information your own by taking it down and adapting it to your interpretation. Okay? Okay. Now by drawing up a table of values, a graph of y equals cos A plus 45 degrees may be plotted as shown in figure 23.22. If y equals cos A is assumed to start at 0, then y equals cos A plus 45 degrees starts 45 degrees earlier, i.e. has a maximum value 45 degrees earlier. Thus, y equals cos A plus 45 degrees is said to lead. So here we are 45 degrees, we have a 45 degrees factor of leading. Okay, it's leading the other waveform by 45 degrees. Generally, a graph of y equals sine A to delta lags y equals sine A by angle delta, and a graph of y equals sine A plus delta leads y equals sine A by angle delta. What that is trying to say is that a graph with a given value will lead or lag a waveform depending upon the angle at which it has been started. And that's my simple interpretation of that. Okay? And here we have the waveform. Okay? So you can see that y equals cos 45 degrees, it's starting 45 degrees. So that is the leading angle, waveform I should say. And figure 23.2. A cosine curve is the same shape as a sine curve, but starts 90 degrees earlier, i.e. leads by 90 degrees. Hence, cos A equals sine A plus 90 degrees. Okay, it is leading in this case. Okay. Right, problem 8. Sketch y equals 5 sine brackets A plus 30 degrees from A equals 0 degrees to A equals 360 degrees. Amplitude equals 5 and period equals 360 divided by 1, which equals 360. 5 sine A plus 30 degrees leads 5 sine A by 30 degrees, i.e. starts 30 degrees earlier. A sketch of y equals 5 sine A plus 30 is shown in figure 23.23. And here we are, the sketch of 23.23. And again, looking back at what's been said, read the information for yourself again. From sketch, amplitude is 5, okay? It's 360 degrees, so you're looking for the waveform to cover 360 degrees from start to finish. And you can see it starts earlier at a given point, but it will still cover 360 degrees. Now, problem 9. Sketch y equals 7 sine to a to del to pi over 3 in the range 0, where a is less than or equal to 0, but it's less than or equal to 360. Now again, I've done enough talking on this already for you, so you should now be able to be familiar with these yourselves, okay? Because it becomes quite repetitious, okay? But in saying that, draw these waves or form blocks for yourself. Do some research, again, get familiar with the calculations for these, okay? Because you will need to know this if you're doing electrical installation or electrical principles at level 3 or above. It is important to remember that pi is equal to 180 degrees. Where pi is divided by 3, the angle becomes 60 degrees. When using your calculator to determine whether you are working in radians or degrees, it matters. You must know whether you're working in radians or degrees, and you need to make sure that that is apparent from your given works as such. Okay? Okay, just making sure that it's all in, okay? Okay. Now problem 10. Sketch y equals 2 cos omega t to 3 pi over 10 over one cycle. Amplitude 2 and period is equal to 2 pi omega rads. 2 cos omega t equals 3 pi over 10 lags 2 cos omega t by 3 pi over 10 omega in seconds. Now a sketch of y equals 2 cos omega t to 3 pi over 10 is shown in figure 23.25. And here we are. Okay. Now again, I don't need to be talking through this again because 3 pi over omega 10 omega rads. So it is 3 pi over 10 omega rads. Okay. That means radians. Right, in problem 1 to 7, state the amplitude and period of the waveform and sketch the curve between 0 degrees and 360 degrees. Okay. Now here I've just simply left you some examples for yourself to work at and look at what information you can gather from online plus and from the electrical principles books. Use them to aid your own style of learning. Okay. And it is only your own style of learning will matter, because it is impossible to accommodate every style of learning, whether you're in school, college, or anywhere else. Okay, you have to make that work your own so that you can understand it. Whether you need to put it on blue paper, pink paper, yellow paper, orange paper, sky blue, or just a hairy fairy, or write it on the back of a fairy if you need to. But you need to understand how your style of learning is acquired and can be appreciated. And these are just examples for you to look at for yourselves. Here I've simply gone through exercise 94 and right, I think these are the answers to some of the questions above. And here we are looking at now sinusoidal form A sine omega t plus minus delta. In figure 23.26, let OR represent a vector that is free to rotate anticlockwise about 0 at a velocity of omega rads per second. A rotating vector is called a phasor. After a time, t seconds, or OR will have turned through an angle omega t radians. Shown as an angle TOR in figure 23.26. If ST is constructed perpendicular to OR, then sine omega t equals ST over OT, i.e. ST equals OT, sine omega t. Please note that is omega t. And this is what I'm talking about here. Okay, we can imagine this being turned clockwise, and it will simply step out the values of the sine wave, climb into its peak value, and begin to drop down as we begin to go through the relevant angles. Okay, and we can plot that out along rotating this here. Okay, and that is the angle omega t. So that angle there will change as we move around. Okay. Now some of you would have seen this already in one form or another, and I recall showing you it in class. Well, some of you it in class if you are doing level 3, and you should be able to plot it as well. Now, if all such vertical components are projected onto a graph of y against omega t, a sine wave results of amplitude OR as shown in section 23.3. If phasor OR makes one revolution, i.e. 2 pi radians in t seconds, then the angular velocity omega equals 2 pi over t rads per second. That gives you the formula to find the rads per second of revolutions, or rotation if you want to make it more liberal. From which t equals 2 pi omega seconds. Okay. T is known as the periodic time, so here we're looking at the periodic time. The number of complete cycles occurring per second is called the frequency, f. So here we have f equals number of cycles over seconds. f equals 1 over t equals omega over 2 pi, which will give you the frequency in hertz. I.e. I've simply repeated that there. Now remember that hence angular velocity omega will give you angular velocity per second. Okay, that means that the rate at which the coils are rotating and cutting that electromagnetic field to generate that AC waveform. Now amplitude is the same, is the name given to the maximum or peak value of a sine wave. As explained in section 23.4, the amplitude of the sine wave shown in figure 23.26 has an amplitude of 1. So we're using 1 as our remit. It's a sine wave, a sine or cosine wave may not always start at 0. To show this, a periodic function is represented by y equals sine omega t plus or minus delta, or y, and that's delta, or y equals cos omega t plus or minus delta, where delta is a phase displacement compared with y equals sine a or y equals cos a. A graph of y equals sine omega t delta lags y equals sine omega t by angle delta, and a graph of y equals sine omega t plus delta leads y equals sine omega t by angle delta. Now, what you need to bear in mind is that you need to sit down and read this information for yourselves, because you're not going to get it once, you're not going to get it twice. You need to apply it 3 and 4 times. For myself, I had to actually go home and write these out and actually begin to do the calculation for myself in respect of the angles and finding sine and cosine and tangent. Especially when you bring in a tangent angle into it, you then need to really know which angles you're talking about. Now the angle omega t is measured in radians, so again make sure you know how to convert degrees to radians. Okay, and as we put it here, i.e. rads over seconds omega t seconds equal omega t radians. Hence angle delta should also be in radians. The relationship between degrees and radians is 360 equals 2 pi radians, or 180 degrees equals pi radians. Hence 1 rad equals 180 divided by pi equals 57.30 degrees, and for example 71 degrees equals 71 times pi over 180 equals 1.239 rads. So we're converting degrees here to radians. So you must be able to convert degrees to radians. Practice, practice, practice. Okay? Now the above gives you information in respect of converting degrees to radians and radians to degrees. Where 1 rad equals 180 over pi equals 57.30 degrees. In this case, remember that pi is equal to 3.142 in its simplified form. To convert degrees to radians, for example, 71 degrees times pi over 180 equals 1.239 rads. So bear that in mind, okay? So summarizing, given a general sinusoidal function, y equals a sine omega t plus or minus delta, then a equals amplitude, omega equals angular velocity, equals 2 pi f rads per second, 2 pi over omega equals periodic time, t in seconds, omega over 2 pi equals frequency, f in hertz, and delta equals angle of lead or lag compared with y equals a sine omega t. Problem 11. An alternating current is given by I equal 30 sine 100 pi t plus 0.27 amperes. Find the amplitude, periodic time, frequency and phase angle in degrees and minutes. Now here I've done the simple calculation. Now you will need to apply this for yourselves and ensure that the valuation comes out to 0.02 seconds or 20 milliseconds. I know this is correct. I've done it myself. Okay, so it should come out correct. The problem some of you have is entering the relevant data into your scientific calculators, because some of you haven't yet learned how to use it. Get used to know your calculator and get it done. When you've done it, show me. Here, I'm not even going to go through this any further, because if you're at level 3 now, this is a simple matter for you to now to calculate, and it should not be an issue. Problem 12. An oscillating mechanism has a maximum displacement of 2.5 meters and a frequency of 60 hertz. At time t equals 0, the displacement is 90 centimeters. Express the displacement in the general form a sine omega t plus or minus delta. And here is the process that we would apply. Amplitude equals maximum displacement equals 2.5 meters. Angular velocity omega equals 2 pi. F equals 2 pi 60 in brackets equals 120 pi rads per second. Now make sure you put into your calculators the information and you arrive at the correct solution. Hence displacement equals 2.5 sine 120 pi t plus delta meters. Okay, now I'm just going to step through this now. Thus displacement equals 2.5 sine 120 pi t plus 0.368 meters. Now make sure you work this through for yourselves and look back at the examples given that we've actually followed through on. And here you have 21 degrees, 6 minutes, which is equal to 0.6368 rads. Okay. And it has done the process for you here, so use it. Okay. Problem 13. The instantaneous value of voltage in an AC circuit at any time t second is given by V equals 340 sine 50 pi t to 0.541 volts. Determine the amplitude, periodic time, frequency and phase angle in degrees. And that's what I'm talking about here. Okay, and here you have A, B, C, D, E. Okay. Now look at the information and extract the information given and take each step in turn and apply the formula for each. Hence periodic time equals T, that's your formula you need to use. This is your formula, use it, okay? T equals 2 pi over omega. Okay. Now I put this here for a reason, but for some reason it has slipped my mind completely why I put it here. It was to highlight a point, but for some reason it has slipped my mind. But it might come back to me in due course. But for the time being, I'm just going to ignore it for now. Okay? But you can then see how to calculate B, and it shows you that process, how to reach here B in regards of the values requested and given. And again, C, similar process. It has given you the formulation here, what you need to do to arrive at this solution. Make sure your answers come out as correct when you put it into your own calculators, because some of you again have to learn to use your calculators. Okay, and that process goes all the way down. Okay, and deal with each step in turn. Do not try to do more than one step at a time. One step at a time, and arrive at that solution steadily. And that would be your waveform. Okay, or should be your waveform. You can see here that the voltage, the peak voltage here, maximum peak voltage here is 340 volts, and that was given in your question. Let me just check that it was given in your question. Okay, let's just go back a little bit and see it was in your question. Okay, yes, okay, here, and it was given you in the question 340 volts. Okay, so that was your peak value. Okay, thank you for your time. I hope you found this useful, and I will look at continuing the mathematical elements in due course. Okay, plus additional information on binary logic and something further on simultaneous equations, so forth. Okay, okay, thank you, and we'll finish there now. Have a good day. Thank you. Bye bye.